Bismillahirrahmanirrahim. Welcome to topic 5.63, Rate Monotonic Scheduling. This algorithm schedules periodic tasks using a static priority policy with preemption. A priority is assigned based on the inverse of its period. The shorter the periods, the higher the priority. The longer the periods, the lower the priority. So we look at the example. Okay, let's say we have two processes, P1 and P2. Period for P1 is 50, and P2 is 100. The processing time for P1 is 20 and 35 for 35, and the processing time for P2 is 35. The deadline for each process requires that it complete its CPU burst by the start of its next period. Or in other words, we can say that the end of a task period is also the task hard deadline. So firstly, we need to measure its CPU utilization. Okay, CPU utilization we consider as the ratio of its burst to its period. Okay, and we have to make sure that the visualizations is less or equal to 1. Okay, so for P1, the CPU utilizations is 20 divided by 50, which is equal to 0.4, and P2 is 35 divided by 100 is equal to 0.35. So for total CPU utilization of both of the processes is 0.75 or equal with 75%. So therefore, it seems we can schedule this task in such a way that both meet their deadlines and still leave the CPU with available cycles. So we want to prove this finding. Okay, so from the period value, we know that the P1 has a higher priority than P2. Okay, so alright, okay, we for rate monotonic scheduling, we call it as a RMS. Okay, so we look at this figure. P1 start first. Okay, P1 start first, so it completes its processing time 20. So at time 20, thereby meeting its first deadline. So P2 starts running at this point and runs until time 50. At this time, it is preempted by P1. So P1 completes its CPU burst at time 70. Okay, at which point the scheduler resumes P2. So P2 completes its CPU burst at time 75, also meeting its first deadline. Okay, the system is idle until time 100 when P1 is scheduled again. Okay, so so from this example, RMS is considered optimal. So now let us next examine a set of processes that cannot be scheduled until using the RMS algorithm. Okay, so we look at the next slide. We assume that process P1 has period of P1 50 and its CPU burst is 25. Okay, for P2, the period is 80 and the processing time is 35. Okay, so the total CPU utilization of the two processors is 0.94 or equal to 74%. Therefore, seems logical that the two processors could be scheduled and still leave the CPU with 6% available time. Okay, so we look at this figure. Initially, P1 runs until okay, so from this example, we can say that P1 has a higher priority according to its period value. Okay, so P1 run until it completes its CPU burst at time 25. Process P2 then begins running and runs until time 50 when it is preempted by P1. Process P1 runs until time 75. Consequently, P2 finishes its burst at time 85 after the deadline for completion of its CPU burst time at time 80. Okay. So despite being optimal, RMS has a limitations, which is CPU utilization is bounded. It is not always possible to maximize CPU resources fully. Thus, we consider the worst case CPU utilizations. Okay, please refer to your textbook how we can calculate the value of worst case CPU utilizations. With two processors, okay, according to our example, CPU utilization is bounded at about 83%. So combined CPU utilization for the previous example for the two processors is 75%. Okay, so therefore the RMS algorithm is guaranteed to schedule them so that they can meet their deadlines. Okay? For our current two processors, combined CPU utilization is approximately 94%. Therefore, RMS cannot guarantee that they can be scheduled so that they meet their deadlines. Yeah, so that is the limitation, the missed deadlines with rate monotonic scheduling. Okay, thank you guys for watching.